Hi, data flow graph architecture is being touted as the preferred choice for efficient AI hardware. Let's dive into some nuances around it. What truly is a data flow graph processor in a true sense? One paradigm is the control flow, where there is a sequence of instructions that execute in a particular program order. However, in this case, graph is the program, and the computation is triggered by the when the data for that computation is available, that computation gets triggered, gets enabled to be executed, contrary to the instruction pointer based approach in the control flow. Now, in 80s and 90s also, a lot of designs were created as a generic data flow graph processor. One thing to note is that there is a very high hardware cost and complexity to implement the data readiness mechanisms in hardware. It also led to the software that is created, the run is extremely difficult to debug. So you would not like to have a true sense data flow graph processor for the Gen AI. It doesn't serve the purpose. We pick the right amount of thing, whatever is needed about it. Let's get into the nuances part. Some interesting things to visualize. Let's start with CPU. CPU is created as a control flow paradigm by large, and it's optimized for the single thread performance, right? However, CPU also implements the data flow graph in its out of order. In the reservation station, there are micro ops that are in flight. The moment one particular micro ops data gets ready, it can get executed out of order. And that aspect is the data flow graph implementation in hardware. However, things are there around it. One, that it's a very costly implementation. And second, it is targeted for single thread performance. That's what the purpose out of order is serving inside the CPU. The limitations that compiler could not know about, this out of order logic is able to push that envelope further to improve the single thread performance. If you see the CPU, uh, a huge portion of the logic in the silicon real estate in it goes towards increasing the single thread performance. The MAC to the overall CPU core silicon ratio, if you see, it'll lie up in the 5 to 25% range, broadly speaking. Then comes the GPU. GPU follows the SIMT paradigm, which is single instruction multiple thread. Basically, the graphics applications are such that one kind of an operation that you're doing on one pixel, similar is happening on the other pixel. So that parallel sequence of operations can be done on a parallel thread as a part of the SIMT. LLM and Gen AI applications, use cases, have one key difference, that they are irregular compared to the graphics. And this, coupled with the fact that Gen AI is also very computational intensive, it kind of makes SIMT not a very ideal uh, candidate architecture choice for the Gen AI use case for the hardware. We'll skip the GPU things for a minute and we'll see the AI accelerator. We'll come back to the GPU later. That's where then for the SIMT limitations, that's where this AI accelerator comes up and it says, hey, and it claims to have no baggage of the SIMT architecture. It says I implement data flow graph processing, kind of near data flow graph processing. Let's try to visualize that. The black line is the time axis, and imagine this green arrow is showing the data flow graph execution. Imagine it's like matrix multiplication followed with some addition, followed with some functions, and then again matrix or something like that. Once this chunk of data flow graph execution is done, then there is another phase, which is called let's call it a prep phase. During this time, preparation is happening for the next phase of next chunk of data flow graph execution. When that gets over, another preparation, and so on. Just for visualization, what this preparation could look like. Imagine if the matrix multiplication has to happen, preparation would involve ensuring that its input tensors are available in the local RAMs, local buffers, and the pointers are rightly pointing to that thing for the data flow graph execution to occur. Now, what will make an efficient AI accelerator? The efficient one will be the one which can maximize the data flow duration, meaning the green arrow width and length can increase. That would be one good thing to have. And the other aspect is the one that can minimize the overheads in this preparation phase. These two things combined make a good hardware. Let's come back to the GPU. If SIMT is not good, how come NVIDIA is winning? Because SIMT aspect, yes, it is inefficient, inoptimal. However, that's overall CPU, the chip performance comes up from a several bunch of factors. And combined, NVIDIA is winning because it's taking a lead over other things. One of them is the stable, robust CUDA ecosystem being one. It has larger chips, it produces the larger memories it uses, and it offers the parallelism, so configurability in this evolving times kind of helps. Let's still get into the nuances in GPU around the data flow graph too. If GPU is running an optimized kernel code, that actually can be effectively visualized as effective as this green arrow that we described below. Similarly, GPU added tensor core slash transformer engines above and beyond CUDA cores. And when an execution is happening in this tensor cores, it is effectively as efficient as the green arrow that we talked about. So finally, amongst all, what Gen AI use case need is parallel, parallel capability and power efficient execution. These two combined, whichever hardware will be leading it out, will be the winner in future. Thank you.